This is the Krebs cycle. It's a loop programmed into the cell to extract energy from all sorts of nutrient sources. But where does it come from? How did nature come up with this design? How does life come up with its programming language? Let's break this question down one step at a time. To be more specific, what I meant by programming language is the processes that the cells use to transform one substance into another. These are what we call pathways in biology. And, like factories, there are small machines along the way that gradually modify your starting material into your end product. These little machines are known as enzymes. So, a pathway is essentially a series of chemical reactions that allow cells to transform one substance, also known as metabolites, into another with the aid of enzymes. I trust that those of you in the audience that know even a little bit of biology have a very similar intuition. I mean, this map is probably what you have in mind when I say pathways, right? In this video, not only am I going to tell you where these come from, but I'm also going to show you why this picture right here is actually incomplete. And by the end of this video, I'll show you how we can tame this evolutionary power for our own uses. Let's get started. To pay homage to the physics-oriented folks in the audience, we're going to be diving into this problem using one of the best ways we know how: first principles. Now, imagine you're a cell trying to survive in a world full of cells, and you happen to be surrounded by a bunch of your other friends. In this world, there are some super special power-up gems floating around, and these gems make you the god amongst your friends. So if you manage to snag one, you gain a ton of power. And only a few of you have acquired such special gems. That makes you guys very adept at surviving in this open world game. But as time passes, you run out of your awesome power-up gems. Boo-hoo. But let's say you happen to have the power, the machinery, to create new power-up gems from the more common gems that are found lying everywhere in your inventory. That would put you back on the pedestal, right? This does come with a catch though. You can run out of these dull gems and as a result, lose your power. So one of you that has a small gem creation method will thrive at this stage. We can keep going and going and going, and voila, we have a pathway. This is what we call the retrograde hypothesis, and Horowitz was the one who came up with it. Isn't it amazing how just from simple first principles thought experiments, you can see how pathways naturally emerge out of this? Except, it's incomplete. Why? Because this hypothesis doesn't explain everything. Let's look at a counter evidence. Back in 1965, Sam Granick was studying how heme and chlorophyll are both synthesides. Heme being the oxygen carrier in your blood and chlorophyll being the light absorber for photosynthesis. If we take the retrograde hypothesis to be true, then heme must have been imported, and the chemicals leading up to heme should not have any ability or significance or advantage, right? They're akin to the dull gems from earlier. Well, that's not what we see here. The molecule before this step can also do what heme and chlorophyll can do, albeit at a slower rate. So, he proposed a new hypothesis. The end product serves a useful function, but a step can be added to further improve the end product again, meaning that the intermediates along the way were once, perhaps themselves, functional end products of a pathway. This is almost the complete opposite of what we had earlier. The most important aspect of this hypothesis, however, doesn't hinge on this, but in the fact that the chemicals themselves, the metabolites, evolve along with the enzymes. So, did pathways build themselves backwards like the first hypothesis, or did they optimize forwards, step by step like the second? They sound equally intuitive, don't they? But the reason that they sound so intuitive is precisely why they're both incomplete, and our skewed intuition comes from one source. Most of us learning biology have an incomplete conception of what proteins and enzymes can actually do. We often think of enzymes as being machines that sit inside of the cell, waiting to do their specific job. We like to imagine them more or less as fixed structures. But this is an incomplete intuition, because a lot of enzymes are, in fact, more like soft moldable clay than hard rigid rocks. A lot of enzymes can have more than one function, and these are known as promiscuous enzymes. The little chemical robot arms inside the enzyme may look very specific for that one enzyme's job, but in reality, it's only optimized for said job in the right environment. These robot arms can be made to do this one reaction type for multiple chemicals that are kind of similar. If you change the structural arrangement around the same robot arm, i.e. the active site, you can alter the reaction being performed. You can totally see this in action in this animation here. Of course, there are limits to this. It's all good if the reactions are related enough, but there are multiple types of chemical reactions, and they require vastly different active sites, so please keep that in mind. In short, this flexible nature of enzymes allows for it to be very versatile, yet optimizable to a certain extent. And you'll see why this is incredibly useful for building pathways in the next two hypotheses. Having the promiscuous nature of enzymes in mind, one can rationalize the patterns from reaction modules such as something called the 𝐎𝐶1 module. What is the 𝐶1 module? It's a big family of reactions that involve elongating molecules by one carbon. The reactions themselves share the same chemistry. Therefore, like different species in evolution, they could have come from the same common ancestor. The ancestor here is assumed to be a generalist that has the active site for this reaction, but it's not geared towards anything just yet. Over time, though, they can be duplicated and evolve in separate trajectories for different tasks. But yet again, this model doesn't explain everything. The evolutionary trajectory can be complicated and full of function gains and losses over time, and the evidence is also hard to come by. In addition, the enzymes can also converge onto the same function, just like how dolphins and sharks look very similar but have completely different ancestries. One other take you can go with, knowing enzyme promiscuity, is that you can make a hypothesis about how new pathways are built. The existence of promiscuous enzymes implies that there is an underground, hidden network of reactions that make, for now, useless chemicals. However, if we force an evolutionary pressure that requires that very useless chemical, the cells that will survive are going to be the ones that have that chemical, even though the enzymes used are very general in the first place. Over time, though, these generalists can become gradually optimized, thus a new pathway is born. This is known as the patchwork hypothesis, and it is the most accepted hypothesis in the community at this point, although it does come with its own chicken and egg problem. If the new pathway comes from parts of old pathways, where do the old pathways come from? So, before I unveil the fully complete model, I think it's very good to recap the previous hypotheses to fully grasp how they connect. Horowitz said that pathways are built backwards since the end product is what is required. End products deplete intermediate, so more enzymes are needed upstream for production. Yet it describes only a few pathways. Granick said that the pathways are actually built forwards. The end products can serve the function, but recruiting additional steps can optimize the product even further. In essence, enzymes and their metabolites evolve together. Yet both of these don't address the true nature of enzymes. Cass and Jensen said that enzymes that share the same reaction type originate from a generalist promiscuous ancestor. This ancestor can duplicate and diverge into their niche pathways. Yet it doesn't really address convergent evolution. Lazcano and Miller said that promiscuous enzymes make hidden connections between pre-existing pathways. These connections make chemicals, and if that chemical is selected for, the proteins get optimized and eventually become their own standalone pathway. Yet it doesn't address how old pathways came to be. These models all sound contradictory, but the last hypothesis I'm about to present actually says, in fact, that all of them are complementary. Isn't learning by deduction cool? It's like a fun puzzle you can play along as opposed to being fed information constantly. And luckily, today's sponsor, Brilliant.org, shares this philosophy of teaching with me. Brilliant is the best way to learn math, data science, and computer science interactively. Brilliant is fun and interactive, with thousands of lessons from basics to advanced topics, and new lessons added every month. Whatever your skill level, Brilliant customizes content to fit your needs and lets you solve at your own pace. In this video, I've talked about protein evolution. This is a huge field that I think what I presented in this video is only the surface of the awesomeness of this field. To get started on the prerequisites of this field, I'd recommend 2 courses on Brilliant. They are Scientific Thinking course, where you can learn how to tackle and break down mysterious puzzles of nature into logical and powerful explanations. And after you've had a go at a few more of the courses, I'd recommend their Computational Biology course. You'll learn how the scientists behind these research papers came to their conclusions, the basics of how information flows inside of a living thing, how organisms are selected for their traits in evolution, the techniques used to determine how similar proteins are, and even how and where these awesome 3D structures I just showed you come from. Beyond computational biology, there are tons of topics on Brilliant that longtime viewers of my channel has been exposed to, such as calculus, linear algebra, and neural networks, all of which come with their cool and beautiful interactives. Don't worry, if you can't solve a certain problem, you can always peek at the explanation. To try everything Brilliant has to offer for free, for a full 30 days, visit brilliant.org/nanorooms or click on the link in the description. The first 200 of you will get a 20% off Brilliant's annual premium subscription. So, after all is said and done, here's the final hypothesis. The essence of how pathways evolve doesn't depend on the metabolite nor the enzyme, but both of them evolving in concert. The hypotheses discussed earlier may be framed as conflicting, but they don't have to be. Especially when there are just 4 different modes for evolution, 4 different ways to do the same thing. Not one of them has to be the only one that's true. How does this happen? As in hypothesis 4, new compounds appear initially as pointless products, where a selective advantage appears for that compound. It makes sense for the enzymes to be recruited. But after all is said and done, those very same enzymes in the pathway can also be promiscuous, which will give rise to even more metabolites in the hidden network. In addition, enzymes aren't the only way to connect these reactions together. You can also connect them using non-enzymatic reactions. These reactions occur on their own without real need for an enzyme. For example, the CO2 leaving reaction helps connect the 2 totally separate pathways together, leading to a new way to make the final product. This leads to an overall incremental expansion of the metabolic network, metabolite and enzyme both, driven by promiscuous enzymes and non-enzymatic reactions. Let's look deeper at an individual recruitment event. Our final hypothesis also introduces one more general way of recruiting enzymes other than forwards or backwards. That is, if a step is limiting the rate of production, there is an incentive to include the enzyme there. If step 2 is slow, then we should include the enzyme there. If there's a pullback, then pull forwards harder. If it's all equal, increase the amount of stuff coming into the pathway. This doesn't conflict with either H1 nor H2, since you can easily have a situation where the initial and the final step can be, well, a slow step. Even though hypothesis 3 and 4 assumes that everything all happens at once, this still demands that each individual gene must be modified, one mutation at a time. But regardless of how they are recruited, like I said, one enzyme can be forced to diverge due to being borrowed or for usage in another emerging pathway. This creates a middle state where the enzyme is a generalist, much like the ancestral enzymes from hypothesis 3. And when they diverge, they're part of the same reaction module, just like the C1 module. So, to recap a little bit, the enzymes evolve along metabolites by means of enzyme promiscuity. The metabolic network can also be connected further by spontaneous non-enzymatic reactions. Recruiting each individual enzyme is a step-by-step process that happens due to a need to optimize how fast the whole pathway is going, or by going forwards or backwards. And finally, during the creation of a new pathway, the shared enzyme can diverge, thus becoming the ancestral enzyme that you see later on. I might have alluded to that this hypothesis is the final end-all be-all. However, there are questions that can still be asked of it. For example, even though it works really well for new pathways, it doesn't completely explain how the core pathways, such as the Krebs cycle, pentose phosphate, or glycolysis come from. Though the hypothesis doesn't fully explain these core pathways, certain parts of their evolution can be explained based on this model. For example, the T in DNA, thymidine, is just one group away from U in RNA. We can hypothesize that T could have evolved from U by means of a promiscuous enzyme's unintended side reaction. And that enzyme later became such a core part of metabolism that DNA uses T instead of U. Furthermore, our understanding of pathways and enzyme evolution isn't purely limited to understanding the past. We can also use it to invent our future. The animation you saw earlier in the video is actually an artificially evolved enzyme in a lab. 10 to 20 generations and you can evolve this enzyme from one function into doing a very different reaction by changing how flexible some of the branches are. This not only gives valuable insight into how we can design enzymes, but it also proves that we can use evolution as a tool to design things, similar to how we can train neural networks. And this brings me to the final point of the video. You might have noticed that these evolutionary hypotheses question one another and create questions in and of themselves, giving a more refined idea of reality as we keep doing so. Just like how you can evolve enzymes and pathways using evolutionary pressures, you can evolve scientific ideas further by asking questions and building off of ideas that came before you. To stand atop the shoulder of giants and reach for the skies. Thank you immensely for watching. Thank you to some of the folks from the Tokuriki lab from MSL UBC for helping out with the making of this video. It has been a great pleasure. この研究は読んで楽しかったです。本当に面白かったです。見てありがとう。